Recording.
Now it is.
Yes. Uh, Good evening, Rahul sir and learners. Welcome once again for the session. Rahul sir, now you can begin the session.
Yes, good evening, one and all present over here, and welcome back again for this subject data structures. So, in our previous session, or in our all the previous sessions, actually, we try to understand the fundamentals behind the data structure, and I guess my screen is visible to everyone. Yes. Okay. So, today we are up to the our last session or last chapter, which is regarding the advanced data structure. So in a today's session, we try to cover the advanced data structures, including the AVL tree, then red-black tree, multi-way search tree, and B tree. Okay, so this topic are included in today's session. Okay. Now, so in a tree, we have seen the different types of trees as well, right? And we have gone through the binary tree, like a tree in which every node is able to have maximum two children, right? Now, again, there was some issues with the binary tree, like where to keep which kind of value in that, or how one can organize the data in the binary tree. Like every node we have to reach and we have to ask whether to put the next value in the left side or right side, right? So that was the issue in the binary tree. Therefore, we try to make it as a value based tree, and we call it as a binary search tree, and which is one of the most usable, or one can say one of the most efficient version of the binary tree. Like the information were kept according to their values. Like if the information is less than the root, then we have tried to keep it into the left subtree, and if the information is greater than the root, then we have kept it into the right subtree. And that's why we named it as a binary search tree, because it is very helpful for the searching operation, right? Now, that binary search tree is also having some of the drawbacks. Like over here, I have taken the two examples. Like you can see in my slide, like if the data is given or entered by the user in particular order, okay, and because of that, the tree will be constructed in a certain different way. Like you can see here, if the data is entered or given by the user in ascending order, like 10, 25, 30, 40, and 50, and it is asked to you to construct the binary search tree, then obviously the first data which is coming, that is 10, so we are keeping it as a root. Then after the data coming is 25. So obviously 25 is greater than 10. So we have kept it into the right subtree of 10, as there were no right subtree for the 10. Okay. Then same rule is, or same logic is followed, and we are ended with this right skew tree. Like it is a tree where there is every node is actually having only right subtrees. Therefore, it is called as right skew tree. And in the opposite version, suppose the data is entered by the user or data is given to you is in the descending order. Okay, like 50, 40, 30, 25, and then 10. Okay, now in this case, what is going to happen every time, whenever you are try to construct the BS tree, then you will observe that as 50 is the maximum value, so 50 will be the root, and next time 40 comes, so 40 is less than 50, so we have kept it into the left side because it is less, and we have to construct it as a binary search tree. Therefore, Next time 30 comes, so obviously it will be kept into the left side, then 25 and then 10. Okay, so we are ended with this left skew tree. So this is actually the drawback of the value based tree, right? If the order of the data is different, because the data will be organized according to its value, isn't it? So if the order is different, then you may end up with the certain different tree. Okay, now let's take the same data like 10, 25, 30, 40, and 50, but the order will be different. Okay, so let us say the first value which is coming is 30. Okay, so we will call it as a root. Now, next value coming is, let's say, 40. So obviously 40 is greater than 30, so we will keep it into the right side. Okay, now let's say next value coming or entered by the user is, let's say, 10. Yes, so the 10 will be the left of 30 because 10 is less than 30. Now the next value coming is, let's say, 25. So obviously it will be kept as a right node of the 10. So the next value we will keep it at the right subtree of the 10. And the last value, let's say it is now 50. Okay. So 50 will be kept over here as a right children of 40. Yes. So same data. Yes. Same data, but the order of organizing that data. If it is different, then we are ended with the some different tree. Okay, this is the drawback one can say of the uh, value based tree. So everything is organized depending upon the value, and because of that there are certain issues, like suppose this is your given tree. Okay, uh, that is right subtree, right skew tree, sorry. Now, in this skew tree, suppose you have to search the element 50. Yes. So, what procedure you will follow? Because we have already seen the searching operation over the tree. So, obviously, you will compare 50 with the 10. As 50 is greater than 10, then you will go to the right. So, right there is 25. So, again, compare 50 with the 25 as it is greater. So, you have to again move towards the right. Okay, and so on. As there are five elements, so we actually required five different comparisons: first comparison, third comparison, fourth comparison, and at the end, fifth comparison, you will find out the yes, the data is there and the element is found. Okay, and the same is applicable for this example also, because suppose you have to search for the 10, then what will happen? You will go and compare it with the every value. Okay, now as of now, as there are only five values, we are requiring five comparisons. Okay, so it is just similar to the linear search, isn't it? We have also seen the complexity of the linear search. As there are n elements, a linear search in a worst case scenario, it produces the big of n complexity. Okay, so this is also applicable to the BSTs. So, the BSTs in their worst case performance, it is closest to the linear search algorithm, that is big of n. Now, why this is happening? Because they are organized depending upon their values. Okay, that is the case. Now, what can be the second observation from this example? Yes. Now, if the data's order was different, let's say after 10, 50 is coming. Okay. So you will obviously put 50 over here. Okay. And then rest of the values, like after 50, 25 is coming. So you will keep 25 in the left of 50. Okay. And after that, let's say 40 is coming. So 40 will be greater than. Yes. So it is organized like this in a BST. Okay. Now you have to search 50. Then what will happen? So first comparison, you will compare with the 10. So as 50 is greater than 10, you will go to the right side. Right side, you will find out 50. So in only two comparisons, you can search the element 50 in my given BST. Same data. Okay. And this is also the one of the skewed version of that BST. Okay. So the second observation that we can find out over here is, if the node is kept away from the root, then it will take more time, right? It will take more time to be get searched because we have to perform certain operations over the data. That is what the foundation or the basis behind the data structure. Okay. So we organize the data because we have to perform the operations on the data. So obviously, while organizing the data, we need to go to that particular place or fetch it from that particular place. Okay, in order to perform certain operations, right? So the second and very important observation that we come up with this example is if your data is far away from the root, so it will take more time to be get searched. Okay. So what we can do? So can we have a mechanism which makes the data closer to the root? Yes, because as there are only five values, right? If you take this example, as there are only five values, but we are getting the time complexity big of n, that is big of 5, if the number of elements are 5. Okay. So if we organize our data in such a way that it is kept or it is distributed closer to the root, like it is distributed very close to the root like this. Okay. Then in that case, what will happen? Then the finding out that data or searching that particular element will be consuming less time, or the complexity of my data structure will be minimized. Okay. Or it will be reduced. Therefore, these two inventors, like these three different persons like Adelson, Welsky, and Landis, they come up with the solution. They try to balance the tree according to its height. Therefore, they named it as a height balanced binary search tree. Okay, and now this height balanced binary search tree is uh, renamed like AVL tree by taking the initial letters of their inventor. Okay, so Adelson, Welsky, and Landis. So they have taken the initials of their names and they have come up with the AVL tree. Now let us try to understand what is AVL tree. So this tree is actually the height balanced. So what that does, what height balancing means? So here they have given one assumption, or they have given one rule, like at every level or at every node, the height of left subtree and the height of right subtree should be, or the difference between the height of left subtree and height of right subtree should be either equal to 1, okay, or it should be 0. Anything more than different than these two values is not permitted. Okay. So if that difference is either 0 or 1, then it is permissible. If you are getting the difference like height of left subtree and height of right subtrees difference, if you are getting it more than 1, right, then the tree is called as unbalanced. Otherwise, tree is called as balanced one. Okay. And that difference is known as balance factor, which is one of the kind of MCQ type of question which most of the time asked in the examination. What is balance factor, or define balance factor? So balance factor is what? It is nothing but the difference between the height of left subtree and height of right subtree. Okay. So which is introduced by this AVL tree. Okay. Now, in order to make the unbalanced tree to balance one, so they have proposed certain rotations. Okay. Now, here you can see I have taken three different examples. Now, here you can see if you concentrate on a node A, so A does not have any left children and right children. So obviously the height of left and right will be 0. So 0 minus 0 is 0. Therefore, the balance factor for the uh, node or vertex A is 0. Similarly, the balance factor for the vertex C is also 0. Now, when you come to this particular node, that is root, in my case B, so the height of left subtree is 1 because there is one edge in the left side, and the height of right subtree is 1 because again there is a one edge in the right side. Okay, so the height of left subtree 1, height of right subtree 1. So if you take the difference between them, then you will getting 0. Okay. So therefore, this tree is now considered as balanced one because it has maintained the balance in the both the subtrees, like in a left subtree as well as right subtree. But if you talk about this example, right now, can anyone tell me how this tree will be constructed? What will be the order of uh, arrival of the elements? Obviously, as C is the root, so C might be have come first in this organization, right? Now, as this is the BST, right? AVL tree's basis is binary search tree. So the values are kept or the information is kept depending upon its value. Okay. So in a ABCD, if you see the A is less than B, B is less than C, and so on. Like that kind of increasing order of alphabet. Okay. So C might have come first. Now the B comes, so B is less than C. That's why we have kept it into the left side. Then after A comes, so A is less than C as well as A is less than B. Therefore, it is the left children of B. Okay. Therefore, till this particular portion, my tree was balanced. Now, after the insertion of A, now my tree is unbalanced. How? Because A does not have any left subtree, right subtree. Therefore, their balance factor is 0. B is having only left subtree, but there is no right subtree. And therefore, I can say the height of left subtree 1 and height of right subtree 0. 1 minus 0 is 1. Okay. Now, if you talk about C, so the C is only having left subtree, but there is no right subtree. Okay. Therefore, the height of left subtree is 2 as there are two edges and height of right subtree is 0. So 2 minus 0 is 2. Okay. And AVL has proposed that the height or the balance factor must be in between 0 and 1 only. If any value other than these two values is considered as the unbalanced tree. So I can say that the C, because of C is getting balance factor 2, my tree is unbalanced or not balanced. And same is applicable over here. Okay. Now here the height of left subtree is 0, height of right subtree is 1. Therefore, 0 minus 1 should be minus 1. Right. But while calculating the balance factor, we used to consider the absolute value. Okay. So you can take it like a mod. This is just a mod of height of left subtree minus height of right subtree. But or for the practice, you can consider it as a minus 1. That is also applicable. Okay. Similarly, here you will get the balance factor minus 2. Yes. Most of the time for the practice or while solving, we take it as a negative because it simplifies our solving. Okay. Yes. Okay. So I hope everyone is getting what is balance factor because depending upon the balance factor, we have to now perform the rotations. Right? Okay. Now let us try to understand the different rotations that we need to perform over the binary search tree in order to make it as a height balance tree, that is AVL tree. Okay. So they have suggested four different kinds of rotation. First one is the single, two of them are the single rotation and two remaining two are the double rotation. Okay. Now when we have to perform which kind of rotation, that we have to understand. Okay. That is our prime motto over here. So the first rotation is left rotation, second is right rotation. These two are the single rotations. Okay. So these first two are our single rotations and these two are the double rotation. That is left rotation followed by right rotation. That is left right rotation and then right rotation followed by the left rotation. That is left, right left rotation. This is also called as LL rotation because it is single left. Okay. And this is also called as right or RR rotation, single right rotation. This is called as LR rotation, left followed by right, and this is also called as RL rotation. Okay, for the sake of simplicity, because every time we are not able to write this entire statement like left rotation, right rotation. So instead of that, we can use the shortcuts. LL for representing the left rotation, RR for representing the right rotation, LR for left right, and RL for right left rotation. Okay. Now, Let us try to understand when we have to perform which kind of rotation. Okay. So the first rotation is single left rotation or LL rotation. Right. Now, while constructing such a kind of tree, let's say first of all A comes. Okay. So A we will consider as a root. Now the uh, A's balance factor will be zero because there is no left subtree, there is no right subtree, so difference will be zero. Now after A, suppose next value comes is B. Okay, so B will be compared with A. So B is greater than A, so it will be kept into the right subtree. Okay, now B's balance factor is zero and A's balance factor will be height of left subtree is 0, height of right subtree is now 1. So I can say it is minus 1 or you can keep it as an absolute value. But for the sake of simplicity, I used to write negative minus 1. So it shows that there is no left, only right is present. Okay. Now suppose till now my tree is balanced. So this is also okay. This is also okay. Okay. Now next is when when uh just a minute. Okay. When C comes, so C will be compared with first A. So C is greater than A. So you have to go to the right. So in a right, B is there. So C obviously will be greater than B. So we have to go to the right of B and keep the C value or organize the C value. Okay. Now again compute the balance factor. Then we observe that the balance factor of my entire tree or the nodes in my tree are now get changed. Balance factor of C is now 0, balance factor of B is minus 1, and A's balance factor is now get changed to minus 2. Okay, now till this, the tree was okay or the tree was balanced. But because of insertion of C, my trees get unbalanced. Yes, so where actually we have inserted. That is the case. And depending upon that, you have to understand which rotation we have to perform. Okay. So where we have actually inserted or which node is actually causing the unbalancing of our tree. The node C is actually causing the unbalancing of the tree. Yes. Or can I say that because of insertion of right subtree, the trees get unbalanced. Sorry. Yes. See where C is inserted? C is actually inserted in the right of right subtree. Yes. And because of that single insertion, my trees get unbalanced. Okay. So when you get the right skewed tree pattern, yes, when you get right skewed tree pattern, you have to perform left rotation. Okay. Now in a left rotation, what we have to do? Yes, we will make the parent as a left children. So B's parent A will now become the left children of B. Okay. Now after performing the rotation, my tree need to be a BST itself first. Okay. So you can see B is a root, A is less than B in the left of B, and C is greater than B in the right of B. So still it is a BST. Okay. This was also a BST. Okay, this version was also BSC. This version was also BST. Yes, because of insertion of the because of insertion in the right of right subtree, if the tree is get unbalanced, then we have to perform the single left rotation. Okay, in order to make it as a balanced one. Now, after single left rotation, I can see my tree is now balanced. Yes, or in other way, you can see that if you are getting such a kind of pattern, like if you are getting right skew tree, then perform the left rotation. Okay. Now moving forward for with the next type of rotation, that is RR rotation. Now because of insertion in the left of left subtree, if the tree is getting unbalanced, that is if you are getting left skew tree pattern, then in that case we have to perform the right rotation, RR rotation or single right rotation. Okay, now here what we have to do? We have to make the parent as a right children of a given node. Now, because of A, actually my tree will be get unbalanced. Yes, because when C was there, so there will be no issue, balance factor of 0. When B is inserted, still my tree was balanced. Now, because of insertion of A, my roots balance factor is get changed to 2, trees get unbalanced. Therefore, we have to perform the rotation. Okay, so the rotation is performed here is the single right rotation or RR rotation. Okay, now here what we have to do, we have to make the parent as a right children. So once the parent has become right children, now you can see the balance factor of every node is now 0. Yes, therefore the tree is now balanced. Okay, so or in simple words or in order to remember, if you are getting left skew tree, perform the right rotation. Okay, or in other words, because of insertion of left as a left node in the left subtree, your tree is getting unbalanced, then we have to perform the right rotation. Yes. Now next, left right rotation. This is the double rotation, that is two types of rotations we have to perform, right? So here let's take the example. Suppose you are getting such a kind of pattern, like first C comes, so tree is balanced, then A comes, tree is still balanced. Now B comes, so B is less than C but greater than A, therefore B will be inserted in the right of A. Now who is A? A is actually a left subtree. Yes, A is a left subtree of C. So because of insertion in the right of left subtree, yes, in the right of left subtree, if the tree is getting unbalanced, then we have to perform the double rotation. Okay, now which double rotation we have to perform over here? So that double rotation is LR rotation, left right rotation. Okay, so first of all, we have to perform the left for rotation first. It means the tree will be rotated towards the left. So B will become the parent and A will become the children. So again, you are getting this kind of pattern, that is left skew tree. And we also know that when left skew tree we are getting, then we have to perform the right rotation. So B will be rotated. Now B will be taking the place of root and C will become the right children. Yes. So when we insert a node in the right of left subtree and because of that insertion, the trees get unbalanced, then we have to perform the left right rotation, that is LR rotation. Okay. I hope you people are getting it. We will take one example, then it will be more clear. Yes. Now next, RL rotation. Now when we have to perform the RL rotation, if the node is inserted in the left of right subtree. And because of that insertion, if the trees get unbalanced, like you can see over here, because of B, the tree will be unbalanced, isn't it? Yes, because we know that in a BST or in a binary tree, the nodes are always inserted as a leaf node. So B will be inserted. Yes. So B will be inserted, and because of insertion of B, my trees get unbalanced. Okay. And now where the B is inserted? B is inserted in the left of whom? C. C is actually a right subtree. Okay. Of A. So in the left of right subtree, insertion is made, and because of that insertion, the trees get unbalanced. Then we have to perform the RL rotation. So first we have to perform the right rotation. So C will be rotated towards the right. That is B is taking a place of C. C will become the left children. Then you will get the right skew tree. And once you get the right skew tree, we have to perform the left rotation that we have just seen. Okay. Now after performing these two double rotations, now my tree is now get balanced. Balance factor of every node is 0. It is not always necessary to have a balance factor of every node to be 0 as a final product. Okay. It can be 0 or 1. Yes, 1 is acceptable. Yeah, 1 is permissible. Okay. Therefore, do not while solving the problems, do not make the uh, many rotations. Okay, most of the time that is what my observation is. If the question is asked in an examination for the 4 marks, right? So ultimately, such a kind of question requires, or the marking scheme of such a kind of question requires 2 3 rotations. Okay, 2 3 at least two or three single rotations and one or two double rotations. Okay, depending upon the marking scheme. Yes. Now let's take the example. Suppose this is what the given data is, right? So we will go and construct the BST, but while constructing the BST, we have to balance it. Okay. So let's move further. So 15, 20. So 15 is the first value. So obviously it will be the root. So the balance factor is 0. Now 20 comes. So 20 as a is greater than 15. So it is the right children of 15. So you will observe that the balance factor of 20 is 0 and balance factor of 15 is 1. So tree is still balanced. Now next time 24 comes, then we can say that the balance factor of 15 will become 2. Yes. And the tree is unbalanced. So obviously we need to perform the rotation. We have to perform the rotation, try to make it balanced one. So as the node is inserted in the right of right subtree, and because of that the trees get unbalanced. Therefore, we have to rotate it towards the, yes, where we have to rotate, we have to perform the single left rotation. Yes. So by making single left rotation, the root will become the left children. So 20 will become a root and 15 will be the left children. Single left rotation. Yes. Now the next value coming is 10. So 10 is greater than, no, 10 is actually less than 20, less than 15. So 10 will be inserted as the left children of 15. Okay. So go and compute the balance factor. So this is 0, this is 0, this is 1. So 2 minus 1, again 1. So tree is balanced. So after insertion of 10, the tree is still balanced. Now after that, 13 comes. So go and compute the balance factor of every node. So this is 0, this is 0, right? This is minus 1, right? So 2 and 0. So this will become 2 and 1, 2, 3. 3 is the height of the left subtree of 20 and 1 is the height of right subtree of 20. So 3 minus 2 will become 2. Yes. So we can say tree is unbalanced. Now what kind of pattern we are getting? Like this. Sorry. Okay. So therefore, we have inserted a node 13 in the right of left subtree, and because of that, the trees get unbalanced. So first of all, we have to perform the left rotation, then followed by right rotation. Okay. So it is actually LR rotation, left followed by right. So after performing the left rotation, yes, my tree will look like 13 will become the root and 10 will become the left children of 13. Yes, but still the tree is unbalanced. So obviously we have to again perform the right rotation. Now after making right rotation over 13, 15 will become the right children and 13 will become the root of that left subtree. Okay, now you can see that the tree is balanced. Yes. So the balance factor of 10 is 0, 15 0, 24 0, 1 minus 1 again 0. So 2 minus 1 it is 1. Okay. So tree is balanced. Now moving forward, let's take the next value to be inserted is 7. So 7 is less than 10. So 7 will be the left of 10. Yes. Now because of this, what is the balance factor? 0, 1, 0, 2 minus 1. Yes, this is 0 actually. Okay. So 2 minus 1, 1, 1, 2, 3. Okay, this is the height of left subtree. So 3 minus 1 is actually 2. So tree is unbalanced. Yes. Now we have to perform the right rotation. Okay. Now when we have to perform the right rotation, we need to take care of this 15 node because 20 is already having a left children, that is 13. So 13 is going to take the place of 20. Okay. So if the 13 is going to take the place of 20, so 15 is greater than 13. So it should be adjusted in the right, in the right subtree only. Okay. So in a right subtree, you will find out the uh, 15 can be placed as a left children of 20. Now the next value is coming 30. So 30 is the greater than 24, so it will be kept into the right subtree. Okay, so tree was still balanced, so we have inserted 36. Now tree is unbalanced, so as we have got the right skew tree pattern, we have to perform the left rotation. Yes, after performing the left rotation, now 30 has become the root, 24 has become the left children. Tree is balanced. Okay, now over here, next value coming is 25, last one in this case. Okay, now go and compute the balance factor of every node. So it is 0, this is 0. Initially, write the balance factor of every leaf as a 0. Then it will be very helpful for you. Okay, 1. Then here 1 0 minus 1, it is minus 1. Then 2 minus 1, it is 1. Then 1 minus 3. 1, 2, 3. 3 is the height of right subtree of 20. So, and 1 is the height of left subtree of 20. So, 1 minus 3, it is minus 2. Okay. Then 2, 1, 2, 3, 4. So, 2 minus 2, it is actually minus 2. Okay. And we have got this kind of pattern after inserting it. See, we have inserted in the right of left subtree. Sorry, we have inserted in the right of left subtree, and because of that, the trees get unbalanced. So we have to perform the double rotation. Zigzag kind of pattern we are getting. That's why we have to perform the double rotation. Okay. Now, after performing that double rotation, we can see that the tree is still unbalanced. Okay. Then, by performing the single left rotation, now my tree is get balanced. Like 24 will become the parent and 20 is now the left children, 15 is the left children as it is. Rest of the things are kept similar. Okay. Now, suppose there are some operations like we have just seen the insert operation and try to construct the BST. Yes. But what about the remove operation or delete operation? Okay. So what we do in a delete operation in the BST? Obviously, we have to find out either the maximum in the left subtree or minimum in the right subtree. Okay, and replace that value. Suppose first we have to delete the 24, sorry, 24. So let's say that we are going for the maximum value in the left subtree. Okay, so this is 24 and this is the left subtree of 24. So here we need to find out maximum or in the left subtree. Okay, so max in the left is 20. So we can replace it with the 24. Okay. So let's say after performing this 24, we have to delete. Okay. So we have to find out maximum in the left subtree. So we have found out that it is 20. So we will replace it with the 24. So after replacement, you can see that the tree is still balanced or not. Yes, it is still balanced. Okay. Now then after, suppose we have to delete the 20 also. Okay, first 24 and then 20. Now, after deleting 24, again, we have used the same logic going for the maximum in the left subtree. So, 20's left subtree is only having one node, that is 15. So, we will keep it as is it is. Okay, so 15 will is going to take the place of 20. Now, you can observe that the tree is unbalanced. Okay, so not only because of insertion, because of deletion also, tree will be get unbalanced. Right? Then also we have to perform the rotation to make it balanced one. Yes. Now, after performing the rotation, like if you keep the 30 as a root and 15 will be the left children, then we can say that the trees get balanced. Okay. Now, next kind of height balanced tree is or the cell balanced tree is that we have to see is the red black tree. Now here again the BST's fundamentals are utilized, but along with that we are using the color property. So every node will be colored either red or black. Okay. Addition to that, there are several requirements of the red black tree. Okay. And those properties are shown over here. So let us explore each and every one of them. So the first property is called as red black property or color property. So here, when the node is inserted, it will be inserted with color. Either or every node is actually having particular color, and there are only two colors permissible. Either it is red or black. Okay. So please keep this in mind, the color property of the red black tree. Second property is called as root property. So if the tree is having root, so root is always colored as black. Okay. Root is always black. Now the leaf property. So every leaf node, including nil or the null node, is black. Right. So every node, suppose it is a leaf node, but still it is having left and right, which is set to null. If we have seen that particular case while implementing the BST. Okay. So that is called as leaf property. The nil nodes are always considered as black. Now, why we have to consider nil nodes, as they are not going to have any value. Okay. That required for the depth property. Okay. So let's move on to the next property, that is called as red property. If the node has a children, right, then the if the red node has a children, then the childrens are always black. If there is a red node, and if that red node is having a children, then it is always black. If it is not, then we have to perform the rotations or recoloring mechanism that we will discuss on the next slide. Okay, so this is the third property, right? So it means there will be no consecutive two reds. Yes, in any path followed from the root to any particular any particular leaf, there should not be any two consecutive red nodes. Yes, so this is called as red property. If there is a red node having any children, then that children must be black. Now the next and last very important property is called as depth property. So for any node or each node, any simple path from this node to any one of its descendant leaf has the same black depth. That is, from a given node, if you are moving towards the left and reaching to the depth of the tree or reaching to any leaf node, then the total number of black nodes encountered in the left side should be equal to the total number of black nodes in the right side. Okay, that's why this leaf property is important. Yes, therefore, this leaf property is important because sometime the total number of black nodes in the left side and right side are not going to match. Therefore, in order to keep them balanced, okay, or it is cell balance, we have to consider that leaf property. Okay, so we have to keep in mind these five different properties of the tree. Then and then only the tree will become a red black tree. Otherwise, it will be just a binary search tree. Okay. Now, why we have to learn this? Because this tree is having good worst case running time for all its operation, like insertion, deletion, any kind of operation that we used to perform. So it is one of the efficient for use to search a particular element, to delete, insert, right? So it produces the complexity in terms of logarithmic. Okay, so the complexity of this red black tree is big of log n, where n is the number of nodes in that tree. Yes. So after following these properties, now you can see that, suppose this is the given example. Okay. So these constraints enforce a critical property of a red black tree is that the longest path from the root node to any leaf node is no more than twice as long as the shortest path from the root to any other leaf in that tree. Okay. And in order to do that, we have to again perform the appropriate rotation and recoloring of the nodes. Okay. Here, I am intentionally using the appropriate rotations word because there are no specific rule for the rotations in the red black tree. We just need to follow all those five properties. Yes, we just need to follow all those five properties. If those five properties are not followed, then we have to either go for the rotation or we have to go for the recoloring. Recoloring means make red as a black, black as a red. Okay, and the rotations will be performed depending upon the rotations that we have seen in the AVL. Right? If you have inserted in the left of left subtree, then we have to perform the right rotation. If you have inserted in the right of right subtree, then we have to perform the left rotation, that kind of rotation. Okay, so there is no specific rule for the rotations that to be followed. Okay, and one more thing, it can be again the uh, rotation followed by the recoloring kind of stuff. Okay, in the red black tree. So this is the given example. Now here you can see there are many nodes. So every null node actually is represented as a black. Now if you follow any path from the root, yes. So let's take this particular path. This is the first path. Suppose I am following, right? So the total number of black nodes are over here is one, right? Now let's take the another path. Now let's take the another path. Suppose this is what the path I am following. Right. Now let's take the third path. Okay. And let's take this is my last one. Now every path you can find out the total number of black nodes are equal. That is one. One, one, one everywhere. Okay. If you count root, then obviously it will be two. From root to any leaf. Okay. And there were no consecutive two red nodes in any path. Like if you go from 16 to 9, so 9 is red, 9 to 7, 7 is black, 7 to 11, 11 is red. Okay. So there are no consecutive red nodes. That is also the property that we have preserved. Okay. Now last kind of tree that we have to explore in this session is multi-way tree. Now, what does that mean? Multi-way. Now, till now, we have seen the trees where a node is able to contain a single value. Okay. Now, we have to generalize this idea and we have to make our tree to able to carry the more than one value. Okay. So an M way or multi-way tree is a tree that has some properties. There are two basic properties of the M way tree. First one is each node in a tree can have at most M children. Okay. Now every node in the tree can have at most M children if the tree of M order is there. Right. Now nodes in the tree can have now most M minus key fields or M minus values, and there will be M pointers which are nothing but the childrens of that node. Right. Now here you can see this is the example that I have taken is the four-way tree. It means every node can have at most four childrens. Now how they will be placed, that we have to understand. Okay, this is the four-way tree. Now, any node in the tree can have at most four children. So minimum will be zero to represent the leaf node. Okay, therefore, and now because of this is the order 4, now my node is able to carry the m minus 1, that is 4 minus 1, three key fields. So this node is now able to carry the three different values. Okay, now what is the benefit of this? Suppose these many values are there 1, 2, 3, 4, again 4 and 2, 10 values are there, right? So for this 10 values organization, right, we have to go up to the level 0th level, first level, second level, third level. Because in the beginning of this session, I have told you that if you are keeping the values away from the root, it will take more time to be get searched or to be get processed. Right? Now our idea is we have to keep the values as close as possible to the root, so that they will be accessed very fast. And because of that, the complexity of my algorithm or complexity of my program will be get reduced. Okay, that is what our ultimate aim. Otherwise, these 10 values can be kept in a right skew tree with the height 10. But here, the height of the tree is maximum 1, 2, 3. 1, 2, 3. Okay. So here you can see the height of my tree is 3. Right. So at most, 3 iterations will be required to process the any one of the node in this tree. Like suppose I wish to process 36. So obviously I will go and search it from 16, like compare it with 16 greater, 27 greater, 45 less, and I have found it. So after 3 comparisons, actually I have got the 36. Okay, so as close as possible to the root, that is what the data organization that we have to make. But for that organization, obviously we need to follow some rules, or we have to build some rules. Okay, so this MWay tree is having two properties. A node can have at most m childrens, and every node will have m minus 1 key fields or values at most within it. Okay, and there will be 4 or m different pointers which are pointing to the childrens of that given node. Okay, so it is defined as the tree that can have more than 2 childrens. If a m-way tree can have maximum m childrens, then this tree is called as multi-way tree of order m, or m-way tree. So this is the pictorial representation with the of the 4-way tree. Now, yes. Okay, now we have understood the m-way tree. Now next part is we have to uh, go for the m-way search tree. Okay, now this m-way search tree is more constrained m-way tree. Like we have applied one more rule to the m-way tree, and we try to make it as a m-way search tree. Okay, and that rule is very similar to the BST's rule, right? Like the information is kept depending upon the values. Yes, or the data is organized depending upon its values, and that constraint is apply to the key fields and values to them. Okay, so the m-way search tree that makes it as a m-way search tree, we have to follow these different rules or different properties. Each node in a tree can associate with the m childrens and m minus 1 key fields. So a node can have maximum m childrens. So here I have given the example of three-way search tree. So a node can have maximum 3 childrens. Okay. So binary tree is actually what kind of tree? Binary tree is actually a two-way tree, right? A node can have two childrens, two ways to go from a particular node. So three-way tree means three different ways to go from a given node. Okay. So from the root, there are three different paths I can reach. Okay. At most. And in a binary tree, every node was having only one value, that is actually 2 minus 1. Right? In a three-way tree, it will be 3 minus 1. A node is able to carry the m minus 1 key fields. Okay. And the rule that we are applying to my m-way tree is the data kept in the node should be in the ascending order, or it is sorted in a ascending order. Like you can see, my root is having a data 11 and 40. So it is sorted. Then the left subtree of the root is having a data 3 and 8. Again, it is in a sorted order. Yes. So the constraint that we are applying to the M-way tree to make it as a M-way search tree is that the data need to be, or the key fields need to be in a ascending order. Okay. The keys in the first k children's are less than the kth key of the node. Like suppose 11 is there. Okay. So in the left of left subtree, or in the left subtree, you can find out 3 and 8, which is less than 11. Okay. But the next key field in my root is 40. Okay. Therefore, the the node with value 30 is kept in between these two. Okay. So the rule is that the keys in the first k children are less than the kth key of the node. Yes, and the key in the last m minus k children, like you can see 55 and 70, are higher than the kth key, like 40. Okay, so 55 and 70 are greater or higher than the 40. Yes, so because of this, the data is arranged in a sorted order. So obviously, the searching or processing of the data will become efficient. It will become more efficient. Yes. Okay. So in a such a tree, M is called the degree of the tree. Note in a binary tree, like we have just discussed. So this is the typical structure of every node in a M-way tree. Okay. So in a structure, in this particular structure, P0, P1, P2, and Pn are actually representing the pointers of the nodes of the subtrees, and K0, K1, K2 up to Kn minus 1 are the key values of the node, right? And all the key values are in a sorted order. It means what? K0 is less than K1, K1 is less than K2, K2 is less than Kn minus 1. Okay, that is for every I, Ki is less than Ki plus 1. Right? So in a M-based search tree, it is not compulsory that every node has exactly M minus 1 values and have exactly M minus subtrees, because obviously it depends upon the number of values that your tree is going to carry. Yes, like you have to maintain, let's say you have to maintain the three-way tree. Okay, and the data entered by the user is only two. So how we can make it as a three-way tree? Because only, let's say, 11 and 14 is given, 11 and 40 is given to you, and the question is asked to make it as a three-way tree. Can we go for more than one level in that case? Obviously not. Yes, because it depends upon the number of data that we are having to be get organized. This, the it is not mandatory in a M-based search tree that every node has exactly M minus 1 values and have exactly M subtrees. Okay. So, in a search trees like the BST, EVL tree, red black tree, etc., every node contains only one value, that is key, and maximum of two children. But there is a special kind of tree, we call it as a B tree, in which the node contains more than one value. Okay, so this is actually the M-way tree, M-way search tree with height balancing property. So B tree is what? This is M-way tree. Basically, along with that, it is a M-way search tree. But not only the M-way search tree, it has also the height balance property. Okay, so it was developed in the 1972 by Baer and McBride. Therefore, by using their initial, they have named it as a B tree. Okay, so initially it was called as height balance M-way search tree, right? So M-way search tree with the balancing property. It means all the left and right subtrees are kept at the same level, or they are maintained at the same level. Okay, so it is later renamed to the B tree. So it can be defined as follows. B tree is a self-balanced search tree in which every node contains a multiple keys and has more than two children. Right. Now here the number of keys in the node and the number of children of a node depends upon the order or degree of the B tree. So every B tree must have some order. Let's take the example, or let's try to understand the properties first for the B tree. So the properties are like, first property, all leaf nodes of the B tree are kept at the same level. Okay, it is not like our red black tree or like AVL tree, where there will be they were permitting that the balance factor can be either 0 or 1. It means one level can be below, or one level can be more, either in the left side or right side. That was permissible. But in a B tree, what we have to follow? The all leaf nodes. If there is a leaf node in a tree, so all the leaf nodes must be kept at the same level, right? And all the nodes except the root must have at least m by 2 minus keys and maximum m minus 1 keys. So this property actually obviously completely derived from the M-based search tree or M-way tree, right? So they have applied one more property that all the nodes except root must have at least m by 2 minus 1 keys. So minimum m by 2 minus 1 keys, maximum m minus 1 keys, as it is property taken from the M-way tree. Okay, and all the non-leaf nodes except root, that is all internal nodes, must have at least m by 2 childrens, like when m is the order of the tree, right? Every node which is internal must have exactly m by 2 childrens. If the root node is a non-leaf node, then it must have at least 2 childrens. If there is a root which is non-leaf, so it should have at least 2 children. At least it means it should be a binary tree at the basis. Now, a non-leaf node with n minus 1 keys must have n number of children. Okay, so that is the same property taken from the M-way tree. All keys in the node must be in the ascending order. So this property is also taken from the M-way search tree. Okay, so by keeping the original properties of the M-way tree, and by adding these two more, like all the nodes except root must have at least m by 2 minus 1 keys, right? And all the non-leaf nodes except root must have at least m by 2 childrens, right? And third property which is added in a B3 is all the leaf nodes must be at the same level. Okay, so let us move forward with this example and try to verify the all those property that we have just seen in the previous slide is followed by my given tree or not. Yes, so the first property was, let's say this is the B tree of the order 4, right? This is B tree of the order 4. So let us cross check each and every, yes, cross check each and every property. So whether all the nodes are in a same level. So yes, second property, all nodes except root must have at least m by 2. So what is the order of my B tree is 4. So m by 2 will be 2 minus 1, 1, right? So 2 minus 1, 1. At least 1 keys and maximum 4 minus 1, that is 3 keys. Okay, so everywhere at least 1 key is there. Okay, and maximum 3 keys, like you can see on the in this node maximum 3 keys are there. Here also 3 keys, right? 3 values are there. Here also 3 values. So second property is followed. Third property, all non-leaf nodes except root, that is all internal nodes. So 1, 2, 3, there are 3 internal nodes, must have at least m by 2 children, minimum m by 2. So m is 4, m by 2 is 2, 4 by 2 is 2, right? So every node is actually having at least 2 children. So here 3 children, 3, 3. Now, fourth property is, if the root node is a non-leaf node, obviously it is, then it must have at least 2 children. So my root is having 3 children. So four properties also followed. For fifth property, a non-leaf node with n minus 1 keys must have n number of children. Yes. So here you can see this node is having how many keys? 2 keys. So it should have 2 plus 1 children. So you can see that this node, internal node, is having 3 children. Again, fifth property is followed by everyone. Huh? Then last property is, all the key values in the node must be in the ascending order. Okay. So you can observe that every value is, or the every node is having a data in a sorted order, in a ascending sorted order. Okay. So this was the last thing or the last topic that we have to discuss, or that we have discussed actually in this session, or in this particular course. Okay, so if you have any particular doubt, you people please ask. Otherwise, that's it from my side. And we try to cover each and every aspect of this course. Okay, if still there are some few, one or two topics might be missing, right? So you can go through with them. If you have any doubt, you can reach me through the Sandeep sir at any time. Okay, that's it from my side. If you have a doubt, then please discuss. Okay, so thank you so much, everyone. Thank you for joining this session. So I am going to end now. Yes. So thanks a lot. Good night and all the best for the upcoming examinations.
Thank you, Rahul sir, for the session. And thank you so
Yes.
much, dear learners, for joining. Good night and take care.
Yes.